Hello everyone, very warm welcome from my side, and welcome to the NB-IoT and LTE-M Learning Week by IoTCreators.com. And I'm Janset from IoTCreators team, and it is really a true pleasure to have you all here. Thank you again for joining. Today we are starting a journey here. As you can see, we are starting our first NB-IoT and LTE-M Learning Week event. We will have 1 to 2 sessions each day, starting from today to next Wednesday until 19th of October. I know many of you registered for all the sessions, but here is an overview of our event calendar. So feel free to join all the other events. They will be hosted in the same environment, so you can use the same link for joining the other events. And I'm very pleased to announce our expert lines of speaker for each sessions. And with that, I would like to introduce today's session and today's speaker. He's Harald Naumann. I think most of you already know him. And today's sessions will be an outlook on the differences in the low power and wide area networks. So Harald Naumann is a recognized IoT and LTE-M evangelist with a primary interest in implementations of wireless applications. He is the author of very well-known IoT and LTE-M cookbook, and he is also the head of business development at Kraut GmbH. And today he will enlighten us and he will show us the way on outlook on the differences in the low power wide area networks. And I know all of you want to hear him now, but before giving the word to him, I just wanted to give you a short information on the housekeeping items. So today's webinar will be 45 minutes plus a Q&A session. And today's presentation will consist of 4 different blocks, and questions will be answered at the end of each block. So questions are highly encouraged. Feel free to ask your questions to Harald, and he will be answering them at the end of each section. This webinar session is recorded and will be sent to you afterwards. And at the end of the webinar, you will be forwarded to a feedback form. So please tell us how it went at the end of the webinar using the feedback form. And now I would like to stop and give the word to Harald.
Hello to everybody. I had the freedom to select different topics, yes, and the main topic is comparing of LPWAN and a little bit outlook in the future. So I'm not showing you the narrowband IoT and LTE-M world only. I show you a little bit from the unlicensed world as well, because I have seen that several of you are already in the unlicensed world and maybe would like to migrate in the licensed world. And there are some differences. Yeah, you have to do a little bit more if you go to the licensed world. I have 4 blocks as told by Janset, yeah, and the first block is the comparison of narrowband LTE-M and outlook on 5G. The second block is about maximum range and real outdoor and indoor coverage. The third block is comparison of the energy consumption. And the fourth block is difference in the antenna design for licensed and unlicensed antennas. And as told in the beginning, I will answer as most as possible questions after each block. And if we have time left in the end of the training, then we go back and answer further questions. So as told, the first part is comparing narrowband IoT and LTE-M. Yeah, first of all, a little bit history. Yeah, we are already in the world of 5G because narrowband IoT and LTE-M are integrated in the 5G world. And we had before the 4G, 3G, 2G, 1G, and 0G. 0G was voice, and I made only 1 slide there for this. The first voice call out of moving vehicles was done in 1918 in Germany. They made phone calls from moving trains to the PSTN phones in Berlin. So you could really dial from the train to the phones in Berlin. They used ultra long band, yes. So they had 192 meters long antennas on the wagon, yeah. and the coupling was done to the telegraph lines parallel to the train tracks. Yeah, a lot of effort for a few phones per day, but it was really possible a long time ago. Yeah, and now direct into Narrowband IoT 1, Narrowband IoT 2, LTE-M 1 and M2. It's a big table, yes, with a lot of figures, yes, and I selected some colors to make it visible. Green is real, yeah, so we have Narrowband IoT 1, we have Narrowband IoT 2, yeah. Gray is something in between. So we had LPWAN in a specification in release 14, but we have today 13, and we have today mainly release 14 in use. And there is narrowband, there is LTE-M, LTE-M M2, but this is totally fantasy. So right now there is no network, there is no chipset, there is no module. So not any specification that we have that we got from 3GPP will go in let's say in mass production or will be used in the networks. A good example is, for example, Narrowband IoT has voice communication with push to talk. I don't see that. Yeah, so I don't see that somebody will activate in a network what is made for voice, a push-to-talk communication. A little bit more fantasy I see in the positioning as well. So we have very nice positioning features inside of Narrowband IoT and LTE-M, but to get it for everybody, yeah, we have to activate it in the network. And activating in the network means licenses. Licenses means costs. And the operator has to get the money back. So I see it critical, yes. So we have already a lot of features inside of narrowband, but we never got it all. A little bit about bandwidth, yeah. So the bandwidth for 12 channels inside of a LTE band is for narrowband IoT 200 kilohertz only. If we go to cut M1, we already need 1.4 megahertz, yes. And if we ever get M2, then we need already 5 megahertz, yes. And M2 is faster, and 2 gives us already slow video options, but okay, it is then already in let's say in competition of LTE cut 1. The narrowband IoT is in general half duplex, and M1 we can run in full duplex. So the speed with M1 is higher, and the energy consumption is close to the same. So the connection to the, let's say, the reattach has a need for amount of energy, and after that, well, we transfer data. If you have to transfer a little bit more data, then N1 is already better than narrowband IoT. Yeah, drop off and reattach. Yeah, in narrowband IoT we have no handover, and this we analyzed with a software tool. Yeah, this software is available for everybody. So if you would like to analyze your local network, then it's fine. The software was developed originally for Deutsche Telekom. You get all the features. Only one feature is missed. It's to click on this nice button here. If this button is active, then you can see where Deutsche Telekom has the base stations, and you can also see the sector antennas. This is not powered on, so but the rest is there. And here you can see we made a trip inside of Lübeck, and the receiving level was falling down, and here we lost the connection. In a short time later, we got the connection again. So there was no handover. There was a few seconds nothing, and after that we have a connection again. So for data communication, this is okay. If you have a short time, if you have no transfer of data. For a voice communication, it would be a mess, because if we communicate by phone, we wouldn't like to have an interrupt in the communication. Yeah, a little bit more about handover or missing handover in narrowband IoT. In narrowband IoT, the base station will try to hold the connection as long as possible. So even there is maybe another base station much closer to the narrowband IoT device, the connection to the former base station will be held as long as possible, and LTE-M will hand over. That means for a moving object, I expect is the energy consumption with LTE-M lower than with narrowband IoT. However, in China, for example, we have no LTE-M in China. They locate everything what is moving on narrowband. It works, but it could be better. Yeah, an outlook on 5G. Inside of 5G, we have the 200 kilohertz for narrowband IoT again. And we also have LTE-M, that means LTE Cat-M, or also called EMTC. And the benefit in 5G is that the operator can change the setting on the fly. In the moment, it's so narrowband IoT and LTE-M is very static here. And with 5G, the operator has a few more options. So they could offer in the night, for example, if they have to transfer a lot of data from, let's say, meters, they could offer more channels, and in the daytime less. These things are possible in a narrowband IoT scenario inside of 5G. Some more, yes. So here you will see release 14, 13, 14, 15, and 16. Yeah. We get more new features. So these new features are here called inside of release 16. So I will spot a little bit in the next slides here. So one we have is some kind of mesh inside the unlicensed band. That means data from a meter could jump to another meter before the data is forwarded to the base station, or a temperature sensor could communicate to the meter, and the meter will communicate to the base station. That means we don't need a direct connect to the base station, so there could be some hops in between. This is something what is promised for the future. Let's see what will happen. Then we have the grain-free transmission. Yeah, this is something what we already know from the world of the unlicensed band. That means devices will transmit data without acknowledgement, yeah, from the IoT device to the base station. Without acknowledgement means data could be lost. However, it will save power. So if we transmit without to ask for permission of sending of data, it will save energy. There, and this is already the last slide in the first block. Before I go over to the next block, I would like to look if there are maybe already some questions. Can you have a look if there is something that I can answer?
Yes, of course, there are some quick questions. So at first, maybe you show the handover map in your page 7. So people are asking, what tool was that? What's a tool that you use for this handing over?
This is no tool. This is a calculation. So
no, the previous one. Sorry, the one.
This one. Yeah, okay.
Yeah, exactly.
This is a tool developed by a business partner, and I have a license on my laptop, so I can explain a little bit. This tool is reading on the layer 1. That means the communication between the module, yeah, and the base station is direct recorded and is going in a database, and the database is then made visible with a lot of screens. So I showed only 2 screens here. Yeah, I could tell the device that I would like to see some more windows. For example, EPCI is the short cell ID. Yeah, so EPCI is repeating inside of Germany several times. But EPCI is in one. Let's say it's in a local region only once a time. Yeah. Then you see here RSSI and RSIQ. Yeah, I selected here the RSP in my view. Yeah, this is available. Yes, I can help with the contact to the development company. So it was very interesting. Yeah, so this trip here was 5 kilometers, and within 5 kilometers we had estimated each kilometer we had on handover. Also, we had no handover. We had a change of the cell ID.
Yeah. Okay. Thank you. And there is a parallel question to that. It says, is it expected for narrowband IoT to support handover on 5G with tech support MMTC?
There is, I go back to this slide here. They call it better mobility, yes. And I made a research and find nothing. So there is no handover. This is related also to the half duplex. So handover is not possible. However, it is not necessary. Yeah. So if you would like to walk your dog and would like to monitor that, if you have, let's say, 2 or 3 seconds or even 10 seconds in between, no connection, have the connection later on, yeah, then you miss maybe. You have no, let's say, no real time. But narrowband IoT was never planned to offer real time.
Yeah, thanks, Harald. And few quick questions more. Is narrowband IoT a 5G technology?
Yes, it is.
Thank you.
So it is a 4G and a 5G technology. Yeah. For narrow, to handle a lot of devices on a small bandwidth. Yeah. We need a technology. And there is no reason to develop the wheel again. Yeah, narrowband IoT will be there. Inside of 5G, they often call it eMTC, but eMTC is nothing else than LTE-M. So the modulation scheme is exactly the same. Yeah. So if somebody is waiting for something new inside of 5G, then they will wait endless. Yeah.
Yeah, exactly. And also parallel to that, the release 15 with that, is it already released by 3GPP? The 15th release.
Could you repeat?
The release 15 is already released by 3GPP.
Yes. Look at here. Yeah, this is not something what that I take from somewhere. So you can see what 3GPP has specified. Yeah. After the specification is then okay. First of all, let's think about what we can do. Then all the members have to agree. If they have agreed, then the software has to be implemented in the networks and in the chipsets, and after that we can buy it. And this is always a delay from, let's say, from the first idea to the final is 3 years, 4 years. So as you can see, if you go backward, how long time we need from release 13 to 14 and from 14 to the, let's say, the first chipsets.
Yeah, let's say good things take time. And lastly, this is about the speed and stationary devices. So which technology is better? Which technology is better for stationary application? Is it NB-IoT or LTE-M?
both is fine. Yeah.
Both is fine.
There is the main difference between narrowband IoT and LTE-M is in the enterprise. Yeah. So you get a narrowband IoT chipset, and that means a narrowband IoT module. You get an estimated half of the price than LTE-M combined devices. Yeah. So if there is a high price pressure, then you end narrowband IoT. Yeah. But if you make a development and would like to sell it, let's say in a big region, then you will end in combined devices because let's say in the States, LTE-M is much better available than narrowband IoT. And if you would like to sell to China, there is no LTE-M, then you have to use narrowband IoT.
Okay, so there are other concerns.
The timers are the same, yeah. I have seen that other people will talk about ERDX, for example, yeah. The timers are the same. The timing, let's say the values of the timers, yeah, there are different. But if you talk about something that should transmit once a day, this you can do with both technologies.
Yeah. And one last question, and the rest maybe we can do it in the second block break. And what is the maximum object speed for LTE-M? Do you have a rough estimation on that? I guess it was in this view image.
We made it on the highway, so we make tests from between Darmstadt and Mannheim. So it isn't that bad what they always promise. Inside the official specification is up to 100 kilometers, but we reach more than 100. Yeah, so this.
Thanks to the no speed limit in German autobahns, I would say.
Yeah, this is a typical German problem. You are right.
Exactly.
Okay.
And there is one question that I could answer. People are asking if this presentations and the recording will be available afterwards. And yes, the session is recorded, and I will share it with the participants afterwards. And the remaining questions, maybe we can handle them in the second break. And I hand over the word to Harald again for the second part of the webinar.
So the next block is a little bit easier to understand. We talk about range and coverage. It's a big difference. Yeah, we have this 704 kilometer range record with LoRaWAN, and I simulated it. Yeah, it is possible. Yeah, so you can simulate the antenna on this side, and you can simulate the antenna in 3.2 kilometers high on the sky, and there's nothing in between. We have mainly free space loss. That means yes, 704 kilometers is possible. Here's another one with 43 kilometers. This I simulated as well, and I can say yes, it works. Yeah. So one antenna was on a mountain, and the other one was on a hill. Nothing in between, so it works. Yeah. So this is nothing special inside of LoRaWAN. We have no synchronization. Yeah, we have no timing signals. It means as long the signal can travel, it will travel. Yeah. Back to a little bit to reality. This is the community of Kirchheim. I selected Kirchheim because I grow up in this region, so I know all the valleys, and I know all the hills, and I know all the villages. Yeah, in the end, it is 12 villages and 12 gateways. Yeah, so Kirchheim with 3,500 people is a little bit bigger. Yeah, it's so big that it is spread in 2 valleys. Yeah, so I had to place two gateways to cover Kirchheim, and in the big valley I could cover 3 villages with 2 gateways. Yes, but a lot of the villages are on the end of a valley, and there is nothing. So that means I had to place always 1 gateway on a high point near of the village to cover the village. Green means I have indoor coverage. Red means I have outdoor coverage, and brown means I have a mix of red and green. That means brown is indoor coverage as well. And yeah, you can see I have some over ranges here, yes, but in the end, yeah, it was if you do it, it is a lot of effort. So it's not that you place one base station on a high mountain and get coverage everywhere. Now you have to place a lot of, yeah. And this is the reality in my city. Yeah. So this you can look in there is a link on the under the picture. This is Neustadt am Rügenberge. This is Neustadt am Rügenberge with 2 gateways outdoor. This is Neustadt am Rügenberge with 2 gateways indoor. Yeah. And this indoor coverage here I made a little bit bigger on the right side, and we have 270 kilometers, but in a diameter estimated, yeah, it is less than 100 meter for indoor coverage from one gateway on a, let's say, a little bit higher building. It's not the highest building because we have now not a lot of high buildings in this nice town. Yeah, to get an indoor, if you see here, this is the area of Neustadt, and here is the indoor coverage. You need a lot of base stations to cover Neustadt with LoRaWAN, yeah. Or you just select narrowband IoT and LTE-M and you are finished. So we have coverage by 3 operators, yeah, with narrowband IoT and LTE-M in the town, yes, and in the middle of the town is a tower with estimated 35 meters by Deutsche Telekom, and outside of the city of Neustadt is another tower with, I think, 55 or 60 meters, and this you can see here, yeah. So this all here is Neustadt. The core city is here with some more base stations. The city of Neustadt is in size, in area, bigger than Munich. Yeah? So to cover not only the core city, to cover all the 30, we have 33 villages that are related to the core city. I think it's impossible. Yeah. So I think it's cheaper to use. That's what we already have. However, we have it. Yeah. Question 2. Let's say coverage and range.
Yes. Let's see. Actually, there is not a question, but a note from a participant that he has decoded narrowband IoT signals at 850 kilometer distance, but without a traffic capability between Madeira and Lisbon. So it is
again, please.
Interesting. He had decoded narrowband IoT signals at 850 kilometer distance. He just wanted to share that it was possible. Yeah.
Yeah. At narrowband, we have, let's say, we have time synchronization. That means if the time synchronization is not working, then we have then signal, but maybe we have no communication. That is the difference to LoRa, because it's non-synchronized. Yeah, we had officially in Australia narrowband IoT range, I think with 100 kilometers guaranteed by the operator, but they tweaked a little bit the base station, so they had to change some settings. Yeah. Okay.
Yeah.
Then we can go over to the next block, and the next block is energy consumption.
Yeah, okay. I mean, actually, there are a few more questions. They're not mainly about the coverage, but since you talk about LoRaWAN, maybe we can handle that. And the rest we do at the end. But a participant asks, is LoRaWAN bidirectional? What are the typical effective data rates and latencies? So maybe some info on LoRaWAN.
As a LoRaWAN cannot be that bidirectional like narrowband IoT, because the base station has, the devices has 1% duty cycle. If you collect some channels together, then you get a little bit more than 1% duty cycle per device. But the base station is limited to 10% duty cycle for all the devices. And if you take 10% of 3,600 seconds, what means 1 hour, then we have 360 seconds for communication for all the devices. If we have 5,000 devices and would like to make an acknowledgement, yes, then we have only 360 seconds left. That means upload, yeah, is much nicer with LoRaWAN than download. So if you would like to work with an acknowledgement with LoRaWAN, then you will run in trouble. It will not work. Yeah. So that is the limitation in the unlicensed band, that you have not enough capacity for the download task. Yeah. And the other question was?
It was, what are the typical effective data rates and latencies with LoRaWAN?
Yeah, so spreading factor 12, that means on the highest link budget, yeah, we talk about 297 bit per second, yeah, so estimated 300, but gross, and if you calculate net, then it's already lower. So it's ultra slow, yeah, and if you are limited to 1%, that means you can send, and then you have to wait a long time before you are allowed to send the next time. So you are limited to 1 hour. It means you can send several times a short block, but then you have to stop the communication for 1 hour. So in a narrowband IoT, you can communicate nearly endless. Yeah. So if there is, the operator will limit you a little bit. Yeah. So on the unlicensed band is normally no limitation, especially on LTE-M. You can, if you can pay it, you can talk around. You can talk around the clock.
Also true. And maybe last question here, Harald, before we proceed. A very important question also for me. Someone asked, what about the myth of deep indoor penetration? Are there now studies which prove the coverage reliability deep indoor?
Yeah, this I can answer on the next slide.
Perfect.
With the energy consumption. At LoRaWAN, we have in the data sheet a sensitivity of minus 137 dBm. Yeah. The other, what the people don't read is LoRa can receive 20 dB under noise floor. The noise floor is in the near of minus 100 dBm. That means at nearly minus 120, minus 112 dBm is the limitation. Yes, you can see that if you read some studies, the minus 137 you reach only in the laboratory. It means the real link budget of LoRaWAN is estimated 15 to 17 to be lower than, let's say, on the marketing slides. Yeah, so there is a difference between marketing and reality. The same we have in narrowband IoT. Nobody will show us the 164 dB link budget in the reality. We stopped in our energy comparison at nearly 154 dB link budget, because we have a jitter of, I think plus minus 5 dB. That means the RSRI and RSRI is jumping up and down. If you go to the limit and jump then lower than 164, then you have a drop off, then you have register to the base station again. So yeah, marketing and reality is different.
Yeah, let's continue to talk about reality then, and I hand over to you for the next section.
Yeah, I go for to the energy consumption. Yeah, this is a slide out of a study that we made for Deutsche Telekom. Yeah, and we analyzed a link budget. I hope you can see that of 134 dB. That means 10 dB higher than 144 and 154. Yeah, link budget, and you can see. And here we have LoRa included, LoRa with 2 packages and LoRa with 3 packages. So we repeated the packet of LoRa once a time or in 2 times. We used 3 times because Sigfox is repeating always 2 telemeter, always sends 3 packages and hope that one of them will arrive. And you can see that let's say at higher link budget, LoRa is a little bit better than narrowband IoT. If we come to 144, then narrowband IoT is already better than LoRa. In this 144 is already a repeating included, so the packet will always repeat it at least once. Yeah, so with narrowband IoT, you can be much surer that your package will arrive. Yeah, and yeah, and if we come to 154 dB link budget, then LoRa is lost because they are limited to, let's say, 142 dB link budget. More is not possible. You can try, you will not achieve it. Yeah, but there is a drawback on narrowband IoT as well. With 10 dB more, we have a need of 15 times more energy. So it's not a free lunch. So you should avoid this region. And 164 dB link budget is even more energy. Yeah. So this you have to understand. As higher the range is, yeah, as higher is the energy consumption. But this is with all LPWAN technologies the same. The exception is Sigfox because they always send the same power level. They don't balance anything. LoRaWAN and narrowband IoT try to balance a little bit the energy consumption in relation to the distance to the base station. Yeah, here the same again. We changed here from 12 byte to 64 byte. Yeah, and if you look here, it was 5,393 dB milliwatt seconds. Yes. And here it is 5,536 milliwatt seconds. So a few bytes more, yes, but the energy consumption is close to the same. And then I calculated it backward. Most of the energy we need for the reattach. Yeah, so it doesn't matter if you send 12 byte or 64 byte or even 500 byte. Most of the energy we lose by the reattach. Yeah, and the same by Deutsche Telekom. Yeah, here is the energy consumption showed by the different CE level. So this CE level 0, 1, and 2, you can translate to 144, 154, and 164 dB link budget. Yeah, and you can see here, for example, send uplink data. As higher the link budget is, as more energy you will consume. Same we have here for the attach procedure. Yeah, as higher the link budget is, as far we are away from the base station, as more energy we will consume. So this and this is exactly telling the same story. And the other way around, somebody asked, what is the speed at LoRaWAN, yes, 297 bit per second. What is the speed with narrowband IoT? Estimated 300 bit per second. It means you as far away from the base station, as slower will be the speed. And here I marked a little bit 3 dB more or less gain. Gain means system gain, antenna gain, yeah. With a good antenna concept, yes, with a good, let's say, planned antenna concept, you can save the most energy, yeah. So planning the antenna right is very important. This is the end at this, let's say, energy consumption. Do you have questions for me?
Of course, I do. If you're not, if you're available still. So, Harald, you mentioned the link budget quite often in this section. So, but can you explain what does the link budget means?
Yeah, there are different words. We have maximum coupling loss. Yeah, we have link budget. Maximum coupling loss is that what we have, what we could theoretical achieve, and link budget is that what we have. That means normally we will not be here. We are something in between. Yeah. So maximum coupling loss, path loss, and link budget are 3 topics that are close together. Yeah, to explain them in detail, I need another slide, but I haven't got.
Yeah, we can maybe share it afterwards, as we discussed earlier, because there's a lot of questions that maybe requires detailed answer. So we can maybe collect them in a text document and share with the participants. But also another question about the power consumption. Can you compare LTE-M to narrowband IoT when it comes to power consumption?
Yes, if somebody has a budget of a few thousand euro, I will do that. So, yeah, the question comes very often. Yeah, and I am looking on internet for studies. Yes, to refer to it if I have an own study, but there is nothing. However, it's not a free lunch. Yes, so let me think about it. Yes, I have one. There is one from a university in Germany, and they come to the conclusion that the energy consumption of LTE-M is lower than narrowband IoT. Let's say from good good link budget to medium link budget. Only if we come to 154 and more, then narrowband IoT is better. So the answer is there is no winner. Yeah. So we should avoid the 164. That means we are already at 154, and at 154, LTE-M will win. But the people can test on their own. The setup and the PCBs we made are public, yeah? But it is days of work, yes, to measure it and to write it together. It's not that easy. So if somebody will pay, yeah, I will do it and I will make it public.
So it is kind of use case specific then also.
Yeah, but it's in the end the same. Yeah. So registering to the base station, the reattach will need more energy than the transmission of the data itself.
Yeah. Okay, I get it. There are a few more questions, but I would say let's proceed with the last one, and the questions we will answer at the end as much as we can. Yeah,
perfect. Yeah, difference of licensed and unlicensed antenna designs here. This, let's say, this topic I have always. If people are coming, let's say, from the Sigfox or LoRaWAN and enter narrowband IoT and LTE-M. I can say a device on LoRaWAN I can make smaller than a narrowband IoT, even if the frequencies are close the same. So LoRaWAN is in this small gap of 7 megahertz. And narrowband IoT have 169 megahertz bandwidth, let's say 170. And if you do the same in US, it is already more or less a little bit if you avoid band 71. However, if you make a device that is covering the whole world, then you need an antenna bandwidth of 357 megahertz. That is the figures. And there is Mr. Chu in 1946. Yeah, he told us, he calculated the maximum radius, yeah, and the maximum diameter of a dipole. Yes, and we use in our designs mainly monopole antennas, and the second part of the monopole, yeah, the antenna has always two parts. The dipole has two radiators, and the monopole has one radiator. And the second part is the PCB itself. It means the length of the PCB is related to the lowest frequency that you can transmit. And if you go to here, you can see with a dipole, I can go down to 2.2 centimeter diameter, and if I do narrowband IoT, I'm already at 7 centimeters. That means a device on narrowband IoT has to be longer. There is no free lunch, yeah. So if you use Chu, then you will see if you really make it small, it will work. But the drawback is that you have minus 3 dB peak gain. That means you can make it smaller, but with the drawback that the gain will be lower. And with narrowband IoT, you cannot go that small. It's impossible. Yeah, these are some examples for €0 antennas. Yes, this is an antenna out of the IoT M2M cookbook, and it's not fantasy. This antenna was in use in the Gillette order button. It is an GSM module inside because the button was developed in a time where there was no narrowband IoT available. However, the bandwidth of this F antenna is already so big that it could cover band 8 and band 20 as well. It was not planned. The target was only band 8, but band 20 was already included. And this one is another shape for another sensor. So it's not the order button, but you can see it is let's say it's close to the same antenna shape, yeah, but already a little bit different, yeah. Somebody of the readers of my book made a copy of this antenna and simulated it and came to the conclusion it cannot work. However, in his simulation was the plastic enclosure not included and the batteries on the back side. So the battery on the back side was 3 AA cells are out of metal, and the metal gives us a little bit ground plane. So the simulation of such an antenna is not that easy. Some more about PCB lengths and antenna efficiency. This is antenna A. This is antenna B. Yeah. Antenna A, I will not name the manufacturer. Yeah. Antenna A was telling us the efficiency at 90, 110, and 130 millimeters. And antenna B was telling us the same, but down to 50 millimeters. Yeah, from 50 millimeters up to 140 millimeters. Yes, and you can see at 100 millimeters length we have an antenna efficiency of 50%. What is the goal? Yeah, and if you go smaller, then the efficiency will shrink. That means we have a higher energy consumption, or we have less range. Yeah. On the other side, here is an antenna planned for narrowband IoT at 400 megahertz. It means one of the bands. It means could be band 8 or band 20. And if I do it on my own, yeah, I'm able to achieve 70% efficiency on 71 millimeters. And if I use a switch between the bands, I can develop a self-made €0 antenna better than a chip antenna. It's only a matter of money and a matter of the effort. So to develop an antenna that you can switch between the bands is a little bit more complicated. Yeah, and this pictures out of the study. The study is already available on the same link than the links before. I got an order to analyze antennas and to make it better. And this nice L antenna is more than 10 years old and was developed by TI. The TI antenna has about 50 ohm. It is in the near of 10 ohm. Yeah, so the impedance is wrong. That is an L antenna. An L antenna has a hand effect. It means if you touch the PCB, then the antenna center frequency will jump a little bit. And here somebody made a sensor. The diameter of the sensor, by the way, was in the near of 70 millimeters as well, like a Gillette button. They copied the L antenna of TI, and yeah, what was happened? They had a hand effect because it was an L antenna. The layout was poor. It means the colors here is showing us that they are deriving a lot of energy, a lot of current in the PCB and not to the antenna. And this is the rework here. In the rework, we have an F antenna included. Yeah, so we have here the feeding point, we have here the shorting point, and moreover, here is the red one is the feeding. There is the shorting point, and the blue bubble here is a capacitor. Here, that means with the capacitor we could switch between 868 megahertz and between 915. So it is not possible to build antenna that is covering the American band and the European band on this small PCB. It's against 2. So we used a switch, and we changed a lot of more things, but all the things that we changed on this PCB are explained in the study. Inside of the study, you will find a link to a database of PCB layouts, and you find quickly 100 mistakes. So everybody is just copying this layout, and there are 2 more layouts that are very popular in copying. If you make a one-to-one copy, then you already made a mistake. Yeah. So it works always a little bit, but not perfect. Yeah. Then I gave the order to my team to simulate. Yeah. And for example, here we changed the distance between the radiator and the ground plane. Here we changed the width of the track to ground. We changed here the length of the PCB. So we changed a lot of things. In the end, we changed 20 different things and showed in the study, if you change something, what will happen. This is only one out of it. So here we changed the width of the track from outward 5 millimeters to 5 millimeters. Yes. The rest of the PCB are the same. And you can see that the center frequency is changing all the time, and that the peak in the return loss was changing as well. Yeah, so one-to-one copy is not a good idea. Yeah, and in the end, I said, okay, take the antenna of TI, yeah, of the design node, take the same space and make it better. And in the study, you will find 4 results that are better than the TI design without to use more bound space. Yeah. This is an F antenna with a bending. This is an F antenna with a meander and a capacitor to switch. This is an S structure. That S structure is in the end an F antenna as well. And this small stuff, what you see here, is a capacitor. So I told my team I would like to have the 0 ohm antenna. So I have perfect 50 ohm at the feeding point without a matching. And we use this small capacitor as a parasitic element here to optimize the 50 ohm as well. And here it's the same like here, but here is the difference that we have a real capacitor in, and we change between 2 capacitors and can then change between 15 megahertz, 860 megahertz. Some more practical examples. So we build a virtual sheep. So we build and develop a tracker on satellite communication and GPS. We developed a street. Yeah, we made flexible antennas. We make simulations. Yeah, it's the same picture like I showed before, but here you can see the floating current. Yeah, and we also measure the antennas in 3 axes to see if the antenna is really radiating. Yeah, and this is a small hint on my next book. So I'm working on a new book. And in the new book, I would like to explain how to develop a wireless IoT device. That means PCB layout, antenna design, a little bit about radio certification, and some more things. Very, very close to hardware, very close to the physics, yeah, and in progress. And in the meantime, I'm offering to all people that are interested in that they can hire me as a consultant for set up a new project, or I'm also explaining remotely how to use the VNA. So with squaring of the machine, I'm able to explain to people far away what they have to do to make, how to match, how to measure, how to calibrate. Yeah, this was the last slide. Yeah, at the end.
Thank you, Harald. It was also great to see your insights on the antennas. We actually do have a couple of questions left from the previous section. Yeah. We're almost at the end, but maybe we can be so quick and then cover those questions as well. So let me try to group them. Some questions about the mesh network. So for mesh narrowband IoT deployment, which frequency will be used? Do you have a view on that?
Yeah, this is in the okay. Narrowband IoT is normally used in the in sub-gigahertz. Yeah, that means if they would like to use the unlicensed band to forward some data, then they will end in Europe at 868 and in US at 950.
Perfect. Actually, there's a kind of a follow-up question on the mesh network. So the participant asked, do you think that low-power wide area networks like NB-IoT, LTE-M, and LoRaWAN could address all the use cases where the proprietary mesh networks are used today? So do you think they can be replaceable and interchangeable?
They can.
They can. They can currently, or they will be able to?
Yeah, this is another slide. I have a present.
Another session.
No, I have a complete comparison of mesh versus narrowband IoT. I have MeshNet on 868 megahertz by NeoCortex, yeah, and the energy consumption in the MeshNet is. So I can run a MeshNet with on 2 AA cells for 7 years by communicating, I think 240 packages per day. Yeah, so narrowband IoT and LTE-M will lose. Yeah, and I see mesh, neo mesh as an extension, as a range extension. That means inside of the building mesh, and outside of the building then narrowband IoT and LTE-M to reduce the energy. Yeah, so the neo mesh has, in comparison to most of the other mesh networks, the router and the gateway and battery. So Bluetooth mesh, for example, has a need for a router, and the router has to be on. The same we have with Zigbee, and the same we have with let's say with 6LoWPAN or Thread. The router is on. That means the router is consuming a lot of energy, and with this special neo mesh, everything is on that.
Yeah, that is perfect to hear. A couple more. So, is it possible to have narrowband IoT connected mode mobility performance like LTE-M in the future? What do you think about that?
Could you repeat?
So now with narrowband IoT, okay, is it possible to have a narrowband IoT connected mode mobility performance like LTE-M in the future? Like
no,
we have to connect, it cannot, right?
Yeah, the drawback of narrowband IoT is the half duplex, yeah, and the next drawback of narrowband IoT is the latency, yeah. So narrowband IoT was never planned as it was in the beginning planned for stationary objects. Yes, this is the beginning of the technology. Yeah. So that's LTE-M has several benefits, and yeah, if you would like to make something moving on LPWAN in China, yes, then you have to accept that there is only narrowband IoT. In Germany, you have the freedom to select between the two worlds.
Yeah, that depends on the location as usual.
Yeah.
Okay, two last questions, and I hope then we will be complete. So how many connections in parallel can be handled in one narrowband IoT cell? Is it still limited?
Yes, the marketing answer is 1 million. Yeah.
Yeah, but let's talk go back to the real life.
The 1 million is true. Yeah, if you have a huge bandwidth. Yeah, so you need a lot of channels. So, but even Deutsche Telekom has it not. Yeah, that means it will be always lower. And in the moment, the planning is 50,000 narrowband IoT connections per cell. Yeah. In the moment, all the operators are using only one block of 200 kilohertz, but they could activate more than one block. This is let's say, it's a luxury problem. If the Deutsche Telekom will run in trouble with 50,000, let's say, registered narrowband IoT base stations in one cell, they will be happy to activate more channels. But at the moment, we are far away from the 50,000. Yeah.
Yeah, of course. Okay, I will finish this session with one last question, because I also don't want to take much time off Harald right now. But Harald, maybe can you tell us how much volume of data is considered reasonable for narrowband IoT and LTE-M? Do you have a starting point for that?
Yes, then I go back in my slides. This was the beginning. Wait a minute here. We have a message container, yes, in the uplink of 2,536 bits, yeah, at narrowband IoT, and we have 2,984 bits at LTE-M. Everything what is smaller than these two values is is physical forwarded in one package. Yeah. So as more data you transmit here, as more you have to pay, as higher is the energy consumption. But the other way around is, let's say, the 50 bytes to 250 bytes are the common, let's say, values for both worlds, for narrowband IoT and LTE-M. Yes, you can do more, but then we are moving far away, let's say, more to LTE Cat 1. Yeah? So the question is, what is the application?
Yeah.
Yeah. So nobody will stop you to transmit more. The only what will be happy is the operator, because they make more money with the application.